Hello everyone, welcome to designing and creating polyhedron models with FreeCAD. Here's a list of topics we will be covering in this video. Previously I have only made videos considering the use of FreeCAD as it relates to 3D printing, but I have recently become interested in designing these neat looking polyhedrons. I've spent a few weeks deriving the equations used for designing these models, and decided the topic was worth sharing. Here's a video showing concept models made from foam board of both designs featured in this video, which have proven to be very interesting night lamps. For this video, you will need to be familiar with the part design workbench, especially as it relates to sketching and padding. In the description, you can find the link to my part design workbench tutorial video for an overview of the features which will be utilized in this video. Before we begin, I should mention that I have included the trigonometric equations I have derived for the design of each model, so that viewers who are interested could use them to create models with their own input parameters. However, the dimensions used to create the example models are listed in the construction walkthroughs, so there is no need to perform the calculations if you do not feel inclined to do so. I'm going to let viewers decide which of my 3D printed projects should be covered in my next FreeCAD video by voting in the comments section. Here's a list of project candidates: a mini USB-powered vacuum cleaner, a right-angle viewfinder for digital cameras with variable magnification, parts for an RC airplane, such as control horns, electronics and battery bays, motor mounts, and shock-absorbing landing gear, or a set of binoculars. The project which gets the most votes will be featured in my next FreeCAD video. Let's get started by taking a look at the design parameters used to create the first model. This model is composed of 4 differing panels in 3 sections. The base triangle and the intermediate rhombus at the point of the base polygon makes up the base section. The flat hexagonal face representing the side of the main polygon makes up the midsection. And lastly, the kite-shaped panel makes up the roof section. A set of each of these panels accounts for one side of the chosen polygon. There are 2 polygons which are used to determine the structure of this model. The main polygon determines the horizontal size of the middle section of the model, while the size of the base polygon, which is dependent upon the number of sides of the main polygon, determines the size of the opening at the bottom of the model as well as the size of the base triangles. The first 2 input parameters to consider for this model are the side length of the main polygon, which we will label as S, and the number of sides of that polygon, which we will designate as N. From these 2 variables, we can calculate the side length of the base polygon, which is equal to a fixed value of S times the cosine of 360 divided by N, indicating that the base side length relative to the main side length is equal to cosine of 360 over N. The axial separation between the main and base polygons is also dependent upon the chosen polygon. For the choice of the input variable n, I recommend a value of 5 or greater. While it is technically true that you can choose to use an n value of 4, the model will turn out more like a diamond, as it will be lacking a base polygon due to the fact that the cosine of 360 divided by 4 is equal to 0. Here are some examples of this model with differing n values. Red represents an n value of 5, orange represents 6, green is 7, and blue is 8. If we view the models from the bottom view, we can examine the relative sizes of the base and main polygons to get an idea of how the n variable affects the outcome of the model. Here are the relative base sizes computed using the base size equation and given in terms of percentage of the main polygon side length S. The pentagon base side is 30.9% the size of the main side, while the hexagon is 50%, the heptagon is 63.35%, and the octagon is 70.71%. For our example, I will be using an n value of 6, meaning that our example polygons will be hexagons, and we will be using an s value of 10. So if you want to scale the size of the example model, you can simply multiply the dimensions and translations of the various faces by a factor of x divided by 10, where x is your desired main hexagon side length. Next, we will take a look at the last input parameter used to determine the outcome of the model, which is either theta or h depending on your preferences. Both of these variables essentially determine the same aspect of the model, but theta is used for a desired angular height, while h is used for a physical height. Theta is the angle between the base polygon and the base triangle minus 90 degrees, with a range of greater than 0 but less than 90, whereas h is the height of the base triangle on the z-axis. Each can be solved in terms of the other using these equations. The choice of which variable to use is based on personal preference, as either can be used to determine the overall height of the model, where capital H is the arbitrary height of the rectangular section of the primary flat face. The choice of theta or h also affects the angle of the intermediate rhombus and the roof panels, which I refer to as phi. Phi is equal to a cot 2 times cosine of 180 over n times cot theta for theta, and a cot 2 times h times the cosecant of 180 over n over s for h. Here's an example of how the selection of theta affects the overall shape of the model. All three models here have the same s and n values, but the blue model has a theta value of 30, the green has a value of 50, and the orange has a value of 60. We can see that a lower theta value results in a taller, apparently slimmer model, while a higher theta results in a shorter, more compact model. For our model, I will use a theta value of 45 degrees, equal to an h value of 4.3301, which will result in a phi value of 30 degrees based on an n value of 6. Once you have chosen your input parameters, the next step is to sketch the main and base polygons. Sketching these polygons is not required, but it will help you get an idea of the relative sizes of the polygons which will end up shaping the model. To sketch the base polygon, create a sketch from the top view with an initial offset of 0 and set the grid snap equal to s over 2 times the cosine of 360 over n times the cosecant of 180 over n, which is equal to 5 for our example model. Next, we will click the arrow next to the Polygon Sketch tool and select the desired polygon. Then click the origin or 0 point of the sketch to create the center of your polygon. The next step is different depending on whether your chosen polygon is even or odd-sided. For even-sided polygons, click the first grid line on the x-axis in order to create your polygon. If you get a strange or inaccurate-looking polygon, like I did here for example, simply press undo and it should fix itself. For odd-sided polygons, click the first grid line on the y-axis in order to create your desired polygon. In order to create the main polygon, set the grid snap equal to s over 2 times the cosecant of 180 divided by n, which is equal to 10 in our example model. Then use the polygon tool like we did before in order to create your main polygon. Remember that even-sided polygons use the first grid line on the x-axis, while odd-sided use the first grid line on the y-axis. Now that we have covered the preliminaries, we can move on to creating the panels. We will start by sketching the base triangle panel by creating a new sketch from the top view. First, we will sketch the x component of the triangle by setting the grid snap equal to s over 2 times the cosine of 360 over n, which is equal to 2.5 for our example. Next, we will sketch a line from the first negative grid line to the first positive grid line on the x-axis. To finish off the triangle, use the line tool to connect to one of the points we just made. Then we will change the grid snap to s over 2 times sine 360 over n times the cosecant of theta, which is equal to 6.1237 for our example. Then make the second point on the line at the first negative grid point in the y-axis. Then make a new line connecting from the new point to the second x point. Now that we have finished the base triangle, we can exit out of the sketch and move it to the correct position. Go into the Edit menu and select Placement, then enter the value negative s over 2 times the cosine of 360 over n times the cotangent of 180 over n, which is equal to negative 4.3301 in our example, into the Y translation box. Then under the Rotation section pull-down menu, select the x-axis and enter the value theta minus 90, which is equal to negative 45 in our example, into the rotation box. Next, we can move on to the intermediate rhombus face by creating a new sketch from the top view. The first value we will be using for grid snapping the x-axis length will be s over 2 times the cosine of 180 over n, which is equal to 4.3301 in our case. After entering this value into the grid snap box, we will use the polyline sketch tool and make the first point on the first negative grid line on the x-axis. Next, we will enter the y-axis length into the grid box, which is equal to s over 2 times sine 180 over n times the cosecant of phi, equal to 5 in the example. Then we will make the second point on the first positive grid line on the y-axis. Next, we will re-enter the x value, which was 4.3301, for our grid snap and make the third point on the first positive grid line on the x-axis. Then re-enter the y value again and make the fourth point on the first negative grid line on the y-axis. Then we will finish the sketch by connecting to the first point we made. Next, we will exit the sketch and move the face to the proper position. Open the placement window again and enter s over 2 times cos squared 180 over n, which is equal to 3.75, into the x translation window, negative s over 2 times cos squared 180 over n times cot 180 over n, which is equal to negative 6.4952, into the y translation window, and h, or s over 2 times sine 360 over n times cot theta, which is equal to 4.3301, into the z translation window. Next, we need to select Euler angles from the rotation pull-down menu and enter 180 over n, which is equal to 30, into the yaw rotation box, and phi minus 90, which is equal to negative 60, into the roll rotation box. Next, we can move on to the primary flat panel. Create a sketch from the front view, which is the x and z plane, and set the grid snap equal to s over 2. Then use the polyline tool to make a line from the first negative to first positive grid line on the x-axis. Next, enter the value of h, or s over 2 times sine 360 over n times cot theta, which is equal to 4.3301 in our example, into the grid snap box. Then make the next point on the first negative grid line on the z-axis. Then finish up the triangle by entering the s over 2 value into the grid snap again, and connect the line to the first point we made on the x-axis. Next, we need to make the rectangular section of this face, which has an axial height of capital H in the z-axis, where capital H can be any arbitrary height you desire for the center portion of this model. To simplify things, I usually use a value of s or a multiple of s over 2, since it makes sketching simpler. So we'll use an example of capital H equals 10, which is equal to s. First, make sure that the grid snap is set to s over 2, which is equal to 5 for our example. Then use the line tool to connect to the first negative point we made on the x-axis. Then enter your capital H value into the grid snap box and make a 90-degree line from the point we just made to the first positive grid line in the z dimension. If you are using a value of capital H which is not equal to s or a multiple of s over 2, make sure there is a straight vertical line constraint when you make this line, otherwise this face will not turn out correctly. Next, we will repeat the same procedure for the other side. To finish this face off, we will use the line tool to connect to the top of the first line we made in positive z space and enter the value h plus capital H into the grid snap box, which is equal to 14.3301 in the example. Then make the second point of the line on the first positive grid line on the z-axis. Next, we will use the line tool and connect it to the first point we just made. Then we will enter the value of capital H into the grid snap box again and connect the line to the other side of the face. Then we will delete the very first line we made in the sketch along the x-axis so we can pad this face later on. Next, we will exit out of the sketch and move it to the correct position. Go into the Edit Placement menu and enter the value negative s over 2 times cot 180 over n into the y translation box, which is equal to negative 8.6603, and the value 2 times h into the z translation box, which is equal to 8.6603 for our example. The final panel we need to create is the roof panel. The easiest way to create this panel is by copying and pasting the intermediate rhombus sketch. Next, enter the pasted sketch and set the grid snap equal to s over 2 times the cosine of 180 over n times the cotangent of 180 over n times the cosecant of phi, which is equal to 15 in our case. Next, drag the upper point located on the y-axis to the first grid line, then exit out of the sketch. In order to move this panel to the proper position, go into the Edit menu and select Placement, then change the Z translation value to 3 times h plus capital H, which is equal to 22.9904 for our example. Next, select Euler angles from the Rotation pull-down menu and change the roll rotation value to 90 minus phi, which is equal to 60 for the example. Now that we have finished sketching all the faces, we can make a pad of each, using whatever value you would like for the panel thickness. For the example, I'm using a pad thickness of 0.1. The only pad direction you will need to reverse is the intermediate rhombus panel. Next, we will use the fusion operation to fuse the 4 faces together. This will create one side of the n-sided polyhedron. Now that we have finished one side, we are going to use a procedure involving copying, fusing, and rotating in order to complete the model. This procedure is different for even and odd-sided polygons, so I will cover the even-sided method first and then address the odd-sided procedure. First, we will copy and paste the original fusion and rotate the copied fusion in the z-axis by 360 over n, which is equal to 60 in the example. Then combine the original fusion with the copied fusion. Next, we will copy and paste the two-sided combined fusion n over 2 minus 1 times, which is equal to 2 for our example, and rotate each one in the z-axis by 2 times k times 360 over n, where k is the copy number of the pasted two-sided fusion. This means that we will rotate the first two-sided copy by 2 times 1 times 360 over 6, which is equal to 120 degrees in the z-axis, and we will rotate the second copy by 2 times 2 times 360 over 6, which is equal to 240 degrees in the z-axis. This will account for all sides of the model. Next, we will use the fusion operation to combine all the copies together in order to complete the model. Here's an outline of this construction technique for even-sided polygons. Step 1. Copy and paste the original fusion and rotate it by 360 over n degrees in the z-axis. Then fuse the pasted fusion with the original fusion. This will give you the first two sides of your polygon. Step 2. Copy and paste the two-sided fusion n over 2 minus 1 times, and rotate each pasted two-sided fusion in the z-axis by 2 times k times 360 over n, where k is the copy number of the pasted two-sided fusion. For instance, if you were using an octagon, you would copy and paste the two-sided fusion 8 over 2 minus 1 equals 3 times. Then rotate the first copy by 2 times 1 times 360 over 8, which is equal to 90 in the z-axis. The second by 2 times 2 times 360 over 8 equals 180 in the z-axis. And the third by 2 times 3 times 360 over 8 equals 270 in the z-axis. Step 3. Fuse all of the two-sided fusions together to complete your model. Next, we will take a look at the odd-sided polygon embodiment of this procedure. Step 1. Copy the original fusion twice and rotate the second copied fusion in the z-axis by 360 over n, and fuse it with the first copied fusion. Then rotate the new subsequent fusion by 360 over n. This will give you a one-sided fusion and a two-sided fusion. Step 2. Copy and paste the two-sided fusion n minus 3 divided by 2 times, and rotate each copy by 360 times 2 times k plus 1 over n, where k is the copy number of each pasted two-sided fusion. Then use the fusion operation to fuse all the fusions together to complete your model. For example, if using a pentagon, copy and paste the original fusion 2 times. Rotate the second pasted fusion in the z-axis by 360 divided by 5 equals 72. Then fuse it with the first pasted fusion. Then rotate this new two-sided fusion in the z-axis by 360 over 5 equals 72. This will give you your first three sides. Then copy and paste the two-sided rotated fusion 5 minus 3 over 2 equals 1 time, and rotate the pasted fusion in the z-axis by 360 times 2 times 1 plus 1 divided by 5 equals 216 degrees. Then use the fusion operation to fuse all the fusions together to complete your model. The second model we will be examining is a bit more complex in terms of design options, despite only having two faces per side: the polygon-shaped base panel and the kite-shaped roof panel. Unlike the prior model where the base size was dependent upon the choice of polygon, the base side length in this model is an independent variable, which we will designate as b. This means that we can use different b values to affect the outcome of the model. Here we can see three different models, all with the same input parameters except their b values. The blue has a value of 0, the green has a value of 0.4 times s, and the orange has a value of 0.6 times s. From this example, we can deduce that the base side length input variable essentially determines how cropped the bottom of the model will be, which in turn impacts the height of the base panel. This means that the b variable can be used to ensure a required opening size at the bottom of the model. For instance, if you are planning on using the model to make a lamp, and the light bulb you wanted to use had a radius of r, then your required minimum base side length would be equal to a value of 2 times r times tan 180 over n. For this model, we have a new input parameter we need to address, which I refer to as z. In the first model, there are two separate panels attached to the base polygon, but in this model there is just a single non-equilateral polygon panel connected to the base. This face has two distinct components: the trapezoidal section connected to the base polygon, and the triangle connecting to the roof at the top. If we examine the design of the model from a top view schematic, we can see the length of this panel on the y-axis is determined by the separation between the base and main polygons. But the division between the trapezoidal and triangle sections is determined by a new polygon, which has a side length equal to z times s, meaning that the z variable is a scaling factor of the main polygon side length. Here we can also see that the shape of this model from the top view actually resembles an irregular polygon with sides numbering twice that of the chosen end value. This polygon has sides spanning from the midpoint of the sides of the S polygon to the points of the Z times S polygon, and is created by the triangular tips of the base panels. Varying the Z factor impacts the overall shape of the model, including the height and shape of the roof section in conjunction with the chosen theta value. Here we can see three embodiments of this model with differing z values. The blue model has a z value of 0.7, the green is 0.8, and the orange represents 0.9. Aside from the obvious height differences, we can also see that the triangular section of the base panel is more pronounced on the z equals 0.7 model compared to the z equals 0.9 model, which is due to the fact that the z variable is directly responsible for the size of the triangular section. These larger triangular tips create a wider gap between the base panels, which in turn affects the height and angle of the roof panels. We can highlight the effects of the z parameter by examining these models from above and comparing their respective z times s polygons. From this perspective, we can also discern the differences in the irregular polygon formed by the z times s and main polygons. The irregular polygon resulting from a z value of 0.7 is hardly noticeable compared to the model with a value of 0.9. If you want to make this polygon a regular equilateral polygon, then use a z value of cos 180 over n. It should be noted that the values of z range from a minimum of greater than cos squared 180 divided by n and a maximum of less than 1, and that the values of b range from greater than or equal to 0 to a maximum of less than or equal to z times s. Also, the minimum n value for this model is equal to 3. Just like before, the variable phi is the angle of the roof, but unlike the previous model, the phi angle used for this model is dependent upon both the z and theta variables. The equation used to calculate phi for this model is equal to a tan 1 minus z times cos 180 over n times cot theta over z minus cos squared 180 divided by n. If you want your theta and phi values to be equal, you can use the following two equations to calculate the necessary z or theta values for a given phi value. For this example, we will be using a b value of 4, an s value of 10, an n value of 5, a z value of 0.8, and a theta value of 36 degrees, which will result in a phi value of approximately 56.8435 degrees. The first step, like before, is to sketch out the three polygons which will serve as the foundation of this model. Again, this step is not necessary, but it makes it simpler to spot a mistake in the future. Just like before, we will create a new sketch from the top view and set the grid snap equal to b over 2 times cosecant 180 over n, which is equal to 3.4026 for the base, z times s over 2 times the cosecant of 180 over n, equal to 6.8052 for the z times s polygon, and s times cosecant 180 over n equal to 8.5065 for the main polygon. Remember that odd-sided polygons are created using the first positive grid line on the y-axis, whereas even-sided polygons use the first grid line on the x-axis. Next we will sketch the base panel, which can prove to be a bit tricky. Create a new sketch from the top view and set the grid snap equal to b over 2 times the cosecant of 180 divided by n, which is equal to a value of 3.4026. Then sketch the polygon on any grid lines which are not on the axes. So for instance, the first grid lines in the x and y planes. We will be moving the shape around, so we don't want the program to lock it to the axes. Next we will do the same thing using the value for the z times s polygon, which was z times s over 2 times the cosecant of 180 over n, equal to 6.8052, making sure to sketch it off the axes just like before. Next we will set the grid snap value equal to b over 2 times cot 180 over n, equal to 2.7528 for the example, and click and drag the center of the base polygon over to the first positive grid line on the y-axis, so that the bottom side of the polygon is on the x-axis. Next, we will set the grid snap equal to b minus z times s times 1 minus sine theta over 2 times cot 180 over n times the cosecant of theta, which is equal to a value of 0.8222 for the example. This value will either be a positive or negative value depending on your design parameters. Next, click the center of the z times s polygon and move it over to the first positive or negative grid line on the y-axis, depending on your value. If your value is positive, use the first positive grid line on the y-axis, and if your value is negative, use the first negative grid line on the y-axis. Next, we will sketch the trapezoidal section of the base panel. Set the grid snap to a value of b divided by 2, equal to 2 for the example, then use the line tool and click the bottom left point of the base polygon. Then turn off the grid snap and create the second point of the line at the bottom left point of the z times s polygon. Then repeat on the right side, making sure that you turn grid snap back on. Next, to sketch the upper triangle section, turn snap to grid back on and set the grid snap equal to s minus b over 2 times cot 180 divided by n times cosecant theta, equal to 7.0249 for the example. Then use the line tool to make a point on the first negative grid line on the y-axis. Then turn off snap to grid and connect it with the lower point of the z times s polygon. When you go to make the second point of these lines, make sure that there is only a dot symbol next to your cursor, not a tangent constraint symbol. If there is a tangent constraint present when you make the line will be connected to the circle instead of the z times s polygon. You might have to zoom in order to ensure this condition. Then turn grid snap back on and repeat with the right side. Now, before we delete the guidelines we used to make this sketch, we will want to go into the Edit Placement menu and move the sketch to the correct position. Enter the value negative b over 2 times cot 180 over n equal to negative 2.7528 into the y translation box. Then choose Euler angles from the rotation pull-down menu and enter the value theta minus 90 into the roll rotation box, which is equal to negative 54 degrees for the example. Next, we will copy and paste this sketch and turn the visibility of one of them off. If you decide later on to change your z or theta value, there is a simple way to update the original face to the new values instead of resketching the entire thing. I'll touch on that in a moment, but first let's finish this panel off. I like to label the sketch with the visibility on with the z and theta values I used to make the face, so I know which sketch is which. Next, go back into the sketch which still has its visibility turned on. Then use Command or Control to select all the lines in the circle of the z times s polygon and delete them. Then select the circle on all sides of the base polygon aside from the side on the x-axis and delete them as well. We have to delete these sketch elements in order to pad the sketch later on. Next, let's take a look at how to update this face if you decide you don't like the initial z or theta values you originally chose. If you want to follow along here, make a copy of the original sketch with the guidelines so you will have a backup. Alright, so let's say you want to change the value of the z variable from 0.8 to 0.7 for example. In order to update this face, go back into the original version of the sketch with the guidelines and enter the new value of the equation b minus z times s times 1 minus sine theta over 2 times cot 180 over n times cosecant theta, which is equal to a value of 1.3049 with our new z equals 0.7 value, into the grid snap box. Then move the center of the z times s polygon to the first grid line on the y-axis, either in the positive or negative direction depending on the value. Next, click the center of the z times s polygon we just moved and then select the lock constraint from the constraint toolbar. This will prevent the program from moving the polygon around when we go to scale it. Next, we will add the updated value we just used with the value z times s over 2 times the cosecant of 180 over n, which is equal to 7.2594 for this example. Then we will enter the result of this summation into the grid snap box. Now we can finish updating this panel by moving the tip of the z times s polygon on the y-axis to the first negative grid point. Then we can delete all the extra guidelines like we did for the original panel. Then rename this new face with the new z value if you so desire. If you wanted to update your theta value from 36 to 45 degrees, for example, while keeping your original z value constant, the first step for updating this face is just like changing the z value. Enter the new value of the b minus z times s times 1 minus sine theta over 2 times cot 180 over n times cosecant theta equation, which is equal to 1.6125 with our updated theta equals 45 degrees value, into the grid snap box. Then move the center of the z times s polygon to the first positive or negative grid line on the y-axis depending on your value. For our example, this value is positive, so we will use the first positive y-axis grid line. Next we will enter the value of the updated s minus b over 2 times cot 180 over n times cosecant theta equation, equal to 5.8395 for the new theta value of 45 degrees, into the grid snap box and move the tip of the triangle section to the first negative grid line on the y-axis. Then delete all the extra guidelines like we did with the prior panels. The last step for updating the face with a new theta value is to change the roll of the face to the updated theta minus 90 value, which would be equal to negative 45 degrees for this example. Next we will take a look at the second kite-shaped roof panel used to construct this model. Create a new sketch from the top view and enter the value s over 2 times cos 180 over n, equal to 4.0451 for the example, into the grid snap box. Then copy this number using Command or Control with C, because we are going to be using it again shortly. Next, use the polyline tool and click the first negative grid line on the x-axis. Next, enter the value s over 2 times cosecant 180 over n times z minus cos squared 180 over n times secant phi, equal to 2.2629 for the example, into the grid snap box and click the first negative grid line on the y-axis in order to complete the first line. Next, highlight the value in the grid snap box and use the Command or Control and V keys to paste the x-axial length we used earlier. Then click the first positive grid line on the x-axis. Next, we will enter the value s over 2 times cos 180 over n times cot 180 over n times secant phi, equal to a value of 10.1797 for the example, into the grid snap box and click the first positive grid line on the y-axis to create the third line. Next, paste the x-axial length into the grid snap box again and connect the last line to the first point we made in the sketch. To move the sketch to the proper position, go into the Edit Placement menu and enter the value s over 2 times cos squared 180 over n, equal to 3.2725, into the x translation box, negative s over 2 times cos squared 180 over n times cot 180 over n, equal to negative 4.5043, into the y translation box, and s minus b over 2 times cot 180 over n times cot theta, equal to 5.6833, into the z translation box. Next, we will select Euler angles from the rotation pull-down menu and enter the value 180 over n, equal to 36 for the example, into the yaw box, and enter the value of phi, equal to 56.8435 for the example, into the roll rotation box. Updating this face with a new z or theta value is much easier than the first panel. Just recalculate the two y-axis equations and drag the points of the kite to the new grid points. The x-axial lengths will stay the same unless you change the s or n values. If you change your z value, the only placement value you will need to update is the roll rotation value, which will be equal to your updated phi variable. If you change your theta value, you will need to change your z translation to its updated value in addition to your new phi value. Now that we have finished sketching both panels, we can go ahead and pad them. The direction for the pad of the base panel will need to be reversed, while the roof panel will be normal. Next, we can use the construction technique we utilized earlier involving fusing and rotating in order to complete this model. The detailed overview of this process was covered at the end of the Model 1 construction guide, so we will only be reviewing this method as it relates to this example. Since the polygon used for the example model is a pentagon, we will need to use the odd-sided version of the construction technique. The first step is to fuse the two panels together. Then we will copy and paste the fusion twice and rotate the second copied fusion in the z-axis by 360 over n, which is equal to 72 degrees for the example. Next, we will select the first and second pasted fusions and fuse them together. Then rotate this new two-sided fusion in the z-axis by 360 over n, which is again equal to 72 degrees. This will give us a one-sided fusion and a two-sided fusion. The next step is to copy and paste the two-sided fusion n-3 over 2 times, which is equal to 1 for this example. Next, we will rotate the two-sided fusion in the z-axis by 360 times 2 times k plus 1 over n, where k is the copy number of each pasted two-sided fusion. For our example, we only copied and pasted this two-sided fusion one time, so our only k value will be 1. Plugging this value into the equation, we end up with a value of 216 degrees. So we will go ahead and rotate the pasted two-sided fusion in the z-axis by 216 degrees. Now that all the sides are accounted for, we can fuse them all together to complete the example model. Hopefully you have enjoyed this video. If viewers find the subject interesting, I will create an additional video detailing the process used to derive the equations for polyhedron models, so you can use the same method to create similar models of your own design. The following section is comprised of reference schematics for each panel used in both models based on the trigonometric equations used in their design. For the first model, the initial offset for each sketch is equal to 0, and the view used to map each sketch is denoted at the top of each slide. Here are the reference schematics for the second model. Both of these sketches are mapped from the top view and have initial offsets of 0.